Thanks for the invitation, Al, and Johannes and Livia. I am talking about, well, I've given, so the title I gave you, Hyperpolygon Spaces Beyond the Movable Code, I'm not sure it's a great title. So one of the consequences of what we do is that we will explore certain spaces where a parameter lies beyond a cone that's isomorphic to the movable cone. And so we can definitely say something nice about that, but it's not. A more honest title is looking at projective crepant resolutions of a particular singularity. So last week I was on the seminar when Tom Coates gave this great talk of, a sweeping vista of a great program that's been going on for many years. So from the sublime perhaps to the ridiculous, this is a much more small result. It's a particular observation about okay, one singularity, or it turns out to be an infinite family of singularities, one of which is C4 mod G. But it does point to future work about Nakajima quiver varieties. Anyways, joint work with Gwyn Bellamy, Steve, Rayan, Travis Schedler, and Hartmut Weiss. And this is work that it's not yet on the archive, but it will be soon. So I'll set the scene. I want to talk about symplectic quotient singularities and their symplectic resolutions. So to start with, let's take a complex vector space of even dimension, and I want to take a finite subgroup G of the symplectic group, and I form the orbifold V mod G as spec of the invariant ring. So G acts on V. I can take the quotient V mod G, and then I can simply perform some sort of resolution of singularities F of that singular space. So following, well, Beauville, he introduced the notion of a variety with symplectic singularities, but one of his sort of archetypal cases was a singularity of this form. So indeed, it is part of his motivating data that these quotient singularities have symplectic singularities. What do we mean? So, G acts on V. So on the smooth look, so G acts with some fixed points, indeed some fixed loci. So in the quotient, if you look at the smooth part, so the symplectic form up on V, it's invariant under the action, so it descends to the smooth locus, and then you can pull that back to X, or indeed to some part of X, and if that extends to a regular form on the whole of X, we call that, we say that the quotient has symplectic singularities, and that's true for all V mod G of this form. But we're especially interested in a slightly stronger condition. So F, so that's just for an arbitrary resolution, F is said to be a symplectic resolution precisely when that pullback, or indeed the extension to X, the whole of X of that pullback, is not only regular, well defined on the whole of X, but it's non-degenerate. And in that case, we say that F has symplectic F is a symplectic resolution. And it turns out that this is rare, but you can already see it's not that hard to prove that symplectic resolutions in this context are precisely equivalent to the notion of a crepant resolution. So a resolution that preserves the canonical class. The canonical class of V mod G is trivial, and pulling that back, we say it's crepant if Kx also has trivial canonical class. So one direction of this implication, I guess from here to here, is very easy, and the other direction needs a little bit of work. But the point is that there are many resolutions F of V mod G. Crepant resolutions ensure that we don't keep on blowing up too much. So it's always a question about, do they exist, and can we construct them, and if so, what can we understand about them? Oh yeah, but just to say, so yeah, Al's asked me to scroll vertically. Apparently that's better for editing purposes, so can't quite show you all that. Maybe should I do that? So yeah, they exist sometimes. So the archetypal case, so when G is a finite subgroup of SL2C or SP2C if you like, then the minimal resolution of that ADE singularity is the motivating example of a crepant resolution. So we certainly know they exist in dimension 2, and those are the only cases in dimension 2. But in general, they're rare. And I want to talk about the families that we know of. And in fact, this is conjectured to be all symplectic resolutions of symplectic quotient singularities. So I'll give you two infinite families. Let's give you the whole page. two infinite families and two exceptional cases. And I want to focus attention on one of those exceptional cases. So in fact, I'm not going to say anything about items 1, 2, and 3. It'll be the fourth example that I focus on. But just to give you the context, this is why perhaps this exceptional, this particular orbifold is worth studying, item number 4. I should also say I'm giving you a collection of symplectic quotients that admit symplectic resolutions. If you take products of these, then you also find a symplectic quotient that admits a symplectic resolution. So any symplectic resolution of a symplectic quotient singularity is something on this list or a product of these. So what is the list? So the first infinite family, it generalizes this minimal resolution we have of our Kleinian or our ADE singularity. And the only extra data is we fix a positive integer n, and then we form the Reith product group, which is a finite subgroup of SP2n. The point is, so gamma acts on C2, take n copies of gamma acting on C2n, and take the quotient, so you've got the product of n copies of C2 mod gamma, but then you let the symmetric group act on those, and that's what this Reith product group is doing. That's what this definition is really giving. This group is set up so that the orbifold is simply the quotient of n copies of C2 mod gamma by the symmetric group action. So it's the symmetric product of this singularity. So this is an orbifold, it's this one, and this is known to have a symplectic resolution, and it's given by the Hilbert scheme of n points on the minimal resolution of C2 mod gamma. That's one symplectic resolution. In fact, there are many, and it was a paper that Gwyn Bellamy and I wrote a couple of years ago, studying all projective symplectic resolutions of this singularity, or singularities in this family. And somehow the moral is that one of the results I'm talking about today is just a generalization of that result to a new example. So that's the first family of symplectic resolutions. The second, let me arrow into a symplectic resolution with which many people are very familiar. So the Hilbert scheme of n-points in the plane, in the affine plane, is well known by this Hilbert chairomorphism. It's known to be a crepant, or if you like, symplectic resolution of the quotient of C2n by the action of the symmetric group. And so this is a situation, we have a symplectic resolution. This is a symplectic quotient singularity, but that's not the example I'm giving you. Because the point is that the representation of Sn here isn't irreducible. So it's really the reflection representation on H, right, which is the sum of the coordinates equals 0. So the complementary, this representation has a complementary one-dimensional representation within there. And so in fact, the minimal, or if you like, the indecomposable symplectic quotient is given by this guy, F. So we let Sn act on this V, which is codimension 2 inside C2n. And then this then is the sort of indecomposable or primitive example of a symplectic resolution. Right, so just saying the second infinite family of symplectic resolutions are also much studied. But there are two cases in dimension 4, one of which I'm interested in. Well, I'm interested in them both, but I've got nothing new to say about number 3. I want to take, so the binary tetrahedral group. This is well known to act on C2. So again, I take that representation of the binary tetrahedral group, which is here expressed as a semi-direct product of the quaternionic group and the cyclic group of order 3. So this is it's known to be a finite subgroup of SL2, but here we take that representation together with its contragradient and produce a representation of G4 that writes it as a symplectic subgroup in acting on C4. This singularity, so it's known to admit a symplectic, so it's a symplectic quotient. It's known to admit a symplectic resolution. That's actually Gwyn Bellamy's thesis. He used techniques studying symplectic reflection algebras. So existence was known, but there was no construction. And it's actually Rayan and Sorger who later gave a concrete algebrogeometric construction. That's the first exceptional case. And here's the one I'm interested in for today. So this again is a group involving the quaternionic group of order 8, but I take the product with a dihedral group of order 8. So I've got a group of order 64, but then I mod out by the common center, which is just generated by minus the identity. This is a group of order 32. It gives me a symplectic quotient in dimension 4. And symplectic resolutions again exist. This is so Gwyn and Travis used similar techniques to show existence. And yeah, Gwyn later counted them and proved there were 84 and more or less, sorry, 84, that's not true. It's dimension 4, 81. But more or less the same time, there's this magical paper, so of Maria Donten-Bury and Jarek Wiśniewski, where they construct all 81 projective crepant resolutions of this singularity by variation of GIT by constructing the Cox ring. So I should say, so they write down the Cox ring of the singularity, and they also write down a ring, which they suggest is the Cox ring, and they actually defer to Jürgen Hausen and Simon Keicher, who go on to prove using computational techniques that it is the Cox ring of X. And then they do, so there's lots of computation. It's a magical paper. There's lots of ideas in there, lots of great computation to actually write down all 81 projected crepant resolutions. So there's just such a lot. There's an awful lot one can understand about Cox rings in this paper. So it's a great construction. So I'm going to say something new about this example, and here's what I'm going to say that's new. I'll try and put both theorems up on the screen. There we are. So the first theorem by Bellamy, myself, Steve Rayan, Travis Schedler, and Hartmut Weiss is that this particular fourfold singularity that is known to admit a symplectic resolution of singularities is isomorphic to a particular Nakajima quiver variety. This will turn out to be a hyperpolygon space when I remind you or tell you what that is. But it's a quiver variety for this particular quiver here. So one central node, 5 external nodes, and the dimension vector, perhaps I should write it. So when we write, Nakajima would write this as M0 of V and W. I'm using X5 of 0. Apologies, but I'll explain why. Our dimension vector is 2, 1, 1, 1, 1, and our framing vector is the 0 vector. So that may be more familiar notation for Nakajima quiver varieties, but I'm going to be calling this X5. So that's just an isomorphism of 2 affine varieties. I note that quiver varieties depend on a stability condition, and that's indicated here, so I'm choosing the 0 stability condition. I'm trying to create an affine variety. But more generally, that given that isomorphism of affine cones, the reason this is interesting, why do we like this? Why is this worthwhile? That once you have an orbifold and you know symplectic resolutions exist, well, we've seen that they can be constructed using Cox ring techniques. The advantage of writing it as an affine Nakajima quiver variety is then you can do variation of GIT quotient, and that's what's going on here. So we know the moment we write this as a quiver variety, that if I can choose a generic parameter, and indeed in this context, this is our choice of stability parameter, perhaps I'll also write on here, this guy is m theta of V and W, just in Nakajima's notation. So this is just variation of GIT quotient for Nakajima quiver varieties. We get projected crepant, or if you like, projective symplectic resolutions of this singularity. The content in one is that we get all of them as quiver varieties. And moreover, we understand variation of GIT quotient. So when we have 2 different parameters that lie in different GIT chambers, then we can understand the wall crossing or the birational changes between these Nakajima quiver varieties explicitly in terms of Mukai flops. And in fact, we do more, so we'll write down the entire movable cone, so we'll understand absolutely all of the birational geometry of these hyperpolygon spaces. And this movable cone will be isomorphic to part of the GIT chamber decomposition. So in some sense, some of this, I mean, the fact that one can write down the movable cone and one can understand wall crossing, this comes out of this very explicit calculation and lovely paper of Maria Donten-Bury and Jarek Wiśniewski. And we're sort of observing it in a different way so that we can say a little bit more on the one hand about the resolutions, but it also means that we're really shedding a lot of light on hyperpolygon spaces. Okay, so that's the setup, and this is perhaps a good moment to pause. Oh, I should say, yeah, Mekaria. So that he wrote, did some work on the string theory side. So looking at the quiver gauge theory, for which this is the Higgs branch. So he's a student of Ami Hanani. Actually, I had dinner with him years ago in London in Imperial after giving a talk, and so we chatted for a bit. And I should have asked him more about his Higgs branch varieties. So the suggestion that this orbifold was a Nakajima quiver variety for a quiver like this has appeared in the literature before, so we make it concrete. But the point is then we exploit it to understand the birational geometry of its crepant resolutions. So that's a good pause for, to invite any questions at this stage. As I say, feel welcome, don't hesitate. So I'm going to do something slightly different. I'm not just going to look at X5, we're going to look at all of them. So hyperpolygon spaces are indexed by a positive integer. So now I've got this quiver with n external vertices. I'm writing here n is greater than or equal to 3, and that's true. In the abstract, I said n was greater than or equal to 4. So it turns out when n is equal to 3, we just get a point. And perhaps I should have been honest and say n is greater than or equal to 3, but I'm not very interested in a point. I'm going to look at this. Now, the key case that I'm most interested in is, of course, n equals 5. But one thing that is worth pointing out here, that when we have n equals 4 external vertices, and I've got the doubled quiver for that graph, and crucially, I've got dimension vector with 2 at the central node and 1 around the outside, you can see that we've got the affine, well, this is the affine Dinkin diagram of type D4 tilde. And when I construct quiver varieties for these things, we're actually going to be reproducing some, and this specific example results of Kronheimer from many years ago. So this is, it sort of puts this class into this family, beginning with an ADE singularity of type D4 in the simplest non-trivial case. Okay, so that's the case n equals 4. I'm especially interested in n equals 5, but let's do n. So I want to talk about quiver varieties for this quiver. So I've already doubled my quiver, so I've got arrows in both directions. Whenever there's one arrow, it has an opposite partner. So we look at the space of representations of this quiver, of this dimension vector 2, 1, 1, 1, 1. And the yoga tells us we create a great big vector space where I first of all look at linear maps for every arrow coming from 2, or the thing with dimension vector 2, and then I add on those with arrows going back to 2. So I create a great big vector space. I allow change of basis at each of these vertices, and of course one of the vertices is corresponds to a vector space of dimension 2. The others are all dimension 1. So I've got all my GL1s here. So this group GLV, it acts, I have a moment map, and then in this setup, we form, here I'm talking about the GIT quotient construction, so I could be talking about hyperkähler quotient construction. I'm staying more algebraic for this talk. So what do? We look at mu inverse of 0, and I take the GIT quotient, so mu inverse of 0, the quotient by GLV, or if you like, I take, for any choice of a character, and here perhaps I should say that theta might be in, so theta is a character of the group GLV. I of course always have to note that there's a one-dimensional scalar subgroup that acts trivially, so the group that acts faithfully is, oops, I'll just underline it, I'll go back to the pointer. So the group that acts faithfully is GLV mod C star. The character group of this is Zn, and I tensor over the rationals when doing GIT, so I can talk about some sort of linear phenomenon. And so this is the quiver variety I care about. so this, so I look at the theta semi-stable locus inside mu inverse of 0, and then I consider the quotient by GLV. So proj of a graded ring built from theta in semi-invariant slices of and its multiples of the coordinate ring of this affine scheme, mu inverse of 0. So that's my xn theta. This is, I'll say it again, you can see that I'm not quite convinced by my choice of notation. So this is m theta of VW for this quiver in Nakajima's notation. But so why x? So I'm going to talk about hyperpolygon spaces. But yeah, briefly, so I guess I've already said this, that in the case n equals 4, then we recover, so C2 mod, this binary dihedral group of order 8. That is due to Kronheimer, his observation that this ADE singularity can be realized as a quiver variety before quiver varieties had been written down. This is the case I care most about, and I'll describe something about this proof later on. But one thing I think that is cute that comes out, so in doing all these families, in allowing n to get larger, that here we have a singularity x6. So in the case n equals 6, that we'll see later on we can count the number of projective crepant resolutions. So here's an example where there are, well, we know how many projective crepant resolutions there are. We also know that they're all linked by Mukai flops. So we'll be able to say things even in higher dimensions that weren't known. But why am I calling this xn theta? Oh, I should note it's telling me that there's bad network quality. Can you still hear me well? Olivia?
Yeah, perfectly.
This is nodding his head. Okay.
So we can see very well. Yeah.
We will carry on regardless. So there's some examples at least of the affine quotients. These have been studied a lot so Kono was the first to study them, then Megumi Harada and Nick Proudfoot and others since. So this, until now, so the study has been carried out for those choices of the stability parameter theta in, well, the positive orthant, and moreover for generic stability parameters, right? So for those parameters for which theta semi-stability and theta stability is the same thing, right? So there's a standard thing with this GIT quotient construction that on this space of parameters, this decomposed, there's a wall and chamber structure on this vector space. And when we're in one of the top dimensional or the interiors of one of the top dimensional cones, then our stability parameter is generic. And then we study wall crossing from there. So when we're generic, and when we're in this positive orthant, then xn theta is called a hyperpolygon space. So it really is just a quiver variety for this particular quiver in this particular dimension vector. But I wanted to say why a hyperpolygon space. So these were introduced by Kono in the 90s. No, I think the paper was actually published in 2000. So as hypercalar quotients, and it was Nick and Megumi who first wrote down, who gave the algebraic description and generalized some of what Kono did. But the point is that these are hypercalar analogues of polygon spaces which have been studied before. Francis Kerwin, Hausmann and Knudsen, and others. So these are quiver variety, or not quiver, let's say, these are moduli spaces of quiver representations. Here I make a distinction between this more general notion of a moduli space of quiver representations due to Alastair King on one hand, and then quiver varieties. I'm deliberately calling them Nakajima quiver varieties. These are constructed from a doubled quiver. So these are spaces with symplectic singularities. So for a doubled quiver, when I've got arrows in both directions, they're Nakajima quiver varieties. But it turns out that the space that was studied before, so this mn theta, a polygon space, so it's a moduli space of n-sided polygons in R3, so piecewise linear curves, where the components of our stability parameter, the theta i's, were the lengths of the edges. I should perhaps draw some picture at this point. There's a bit too much on this slide to be drawing a picture, isn't there? I'll zoom in to here. So a polygon in R3, oh, is this going to work if it should work beautifully if I do this piecewise linear thing, shouldn't it? Oh yes, right. So 1, 2, 3, 4, however many. So the point is that the length θ1 would be the length of the first edge and θ2 was the length of the second edge, and so on. And that's the type of thing that was being parameterized by mn theta. And perhaps it makes the point, I've emphasized this to say, this is why one was interested in parameters in this orthant, right? Because the theta i's better be greater than or equal to 0 because they're edge lengths. And I should draw attention to what I've actually written here, I've not said it yet, that inside xn theta, then one of the irreducible components of the core of this variety, this xn theta, and it's the core that allows you, so its irreducible components are compact, allows you to compute things about cohomology and so on. Mn theta is one of these irreducible components. And in fact, you can this at least makes sense, that mn theta is what you get, if I go back to the quiver, if you scrub out all of the arrows going, oops, oh, let's actually scrub them out, let's be bold. All of the arrows going back in to the central node, then the moduli space you get for that is exactly the mn theta. And so it's clearly a subvariety. It turns out to be quite an interesting subvariety. Okay, so these are the hyperpolygon spaces. And so they've been studied before. So in fact, Connor's work, perhaps the main result of his paper, in addition to constructing these, so he proved Kerwin's surjectivity for this class of hyperkähler varieties that was subsequently generalized by McGurty-Nevins, so for all Nakajima quiver varieties. So understanding the cohomology of the hyperkähler quotient in terms of the equivariant cohomology of the master space. Okay, so now let's say a little bit new. I've talked about this space of stability conditions. Now I'm going to tell you explicitly what that wall and chamber decomposition is. So I give you here a collection of hyperplanes. So the coordinate hyperplanes I'm going to index, I'm going to call them hi for I, an integer between 1 and n. And I'm also going to talk about hyperplanes h capital I, where I is a subset of set 1 through n. And I only fix that I contains 1. This is just to make sure we don't include certain things twice. So I include a different collection of hyperplanes. So I've got some hyperplane arrangement. And the point what this proposition says, so the following are equivalent, that in 2 we're saying these thetas satisfying 2 are the generic ones. So these are the ones lying inside chambers. And then, of course, in 1, we're saying that the interiors of chambers are given by the complements of these hyperplanes. So I've got some hyperplane arrangement, and the GIT chambers are the connected components of the complement. Okay, I'm working in QN. Sorry, I should work over the reals if I'm going to say connected components, but the picture in your mind is the same. Okay, so this hyperplane arrangement encodes the GIT chamber decomposition, and part 3 has some content that when I move theta into one of these chambers, so as long as I stay off these hyperplanes, then we get a projective symplectic resolution. So it's actually smooth, this hyperpolygon space. Okay, so I've got some stability space. At the origin, I have this affine quotient, and when I move into chambers, I get some projective symplectic resolution. And a few things to say. Yeah, we know the dimension of these things. Nakajima quiver varieties, you can compute the dimension just by purely combinatorially, and here it's 2 times n minus 6. And as a reality check, when n is 5, we should expect to get a 4-fold. Notice also that the positive orthant, this bit that I've said before, yeah, it's a union of closures of GIT chambers. Or to put it another way, so its supporting hyperplanes are in my hyperplane arrangement. And so none of these pass through F, but some of these second guys do. So F is a union of closures that some of these hyperplanes cut it, and F will be cut into some collection of cones. So indeed F, I want you to think about F as a fan in the sense of toric geometry. It's a simplicial cone, but it's sliced up by hyperplanes in some way. And I definitely have to mention work from not quite 10 years ago, Godinho and Mandini, have studied variation of GIT quotient for hyperpolygon spaces. So for generic parameters, so for these smooth hyperpolygon spaces. And they do this by reducing to or building on work of Michael Thaddeus, so on moduli spaces of parabolic Higgs bundles. So there's a lot of input into this. So anything I say about variation of GIT quotient, the results are out there, and we're just going to give a different and perhaps simpler take on how to interpret variation of GIT. Okay, so we've got our chamber structure, and now let me arrow towards the key statement of the first main theorem. So for now, I'm going to fix a GIT chamber C+. This is largely, it's not very important. I just want to pin down one particular resolution, one particular symplectic resolution. I'm just choosing basically any chamber inside F. I've chosen a particular one. Yeah, notice this is contained in F, but this is a particular chamber of interest. So I can fix one particular projective crepant resolution of this singularity. So I'll just call that X from now on, just so I don't have to keep saying N. I'm doing this largely because at the bottom of the page I want to talk about the relative Néron-Severi space, and I want, if I've got Nx, Xn theta, and plus and Yn0, it's just going to look an absolute nightmare. So we fix one resolution. And I want to make the point that these hyperpolygon spaces are quiver varieties. In particular, right, so every point on this variety, it exists precisely because there's a representation of the quiver I wrote down. And so the universal family is up on our vector space. So in our space of representations, and indeed on mu inverse of 0, the vertices in this quiver fix for us, say, a two-dimensional vector space at the central node, or one-dimensional vector spaces around them. And as we move around the representation space, this vector space moves. And indeed, on mu inverse of 0, we get some G-equivariant bundle upstairs that descends to some vector bundle on our GIT quotient. We get one of these for each vertex of the quiver, and the rank. Oh, I can get right. Something was on the screen telling me. So the rank of these bundles is just given by, or is determined by our choice of dimension vector at the start. So we've got a rank 2 bundle given by our central node, and line bundles given by the others. And there's one point in all this story which one always has to be aware of, that I told you that the diagonal scalar subgroup of GLV acts trivially. Let's say diagonal. That acts trivially. So when I form my GIT quotient, these vector bundles descend, but there's always some I've always got to fix some normalization whenever we talk about quiver moduli spaces in the sense of Alastair King. And I'm going to fix my normalization so that perhaps perversely, or maybe this is the only natural thing to do, the determinant, so the second wedge of the rank 2 bundle, I'm going to insist is the trivial line bundle. I've got to choose something, and that's the one I choose. It turns out that this choice fits together naturally with our choice of parameters that have appeared in the literature before. So the stability parameter space is really hyperplane in an n+1 dimensional vector space, and this choice means that that hyperplane is going to be identified with the Qn. Okay, so the key input that we bring to this story in studying these hyperpolygon spaces is the linearization map. So given a GIT parameter theta, theta is a tuple, an n tuple from components theta 1 through theta n, and I use these as exponents on, well, typically I take the tensor product of the determinants of the tautological bundles, but notice that he's already trivial and these are all line bundles anyway. So I have some line bundle on my GIT quotient on X for every choice of theta. And here I'm working in the relative Néron-Severi space. It turns out that this is isomorphic to not only, I'll write all of them. So the Néron-Severi space itself to the Picard group, or even, if you like, via the first Chern class to H2x of Q. Oh, I should tensor everything by, I should tensor pick by the rationals. So you can think about the line bundle, or if you prefer, you can think about the first Chern class of this line bundle. These are all the same thing. But the reason for my talking about numerical equivalence classes, this is the space where the ample cone really lives, and the Neff cone and movable cone and so on. So that's a very natural map for such a GIT quotient, and that's the guy I'm going to use to help me probe the birational geometry of these spaces. Perhaps I'll leave it there for now. So now I get on to say a bit more about these two theorems I've mentioned up front. I stated the theorems only for the n = 5 case. Here I give Theorem 2 for the general n case. So this is a more general statement than the one I wrote before. And this generalizes, this early work that Gwyn Bellamy and I wrote for the Reith product quotients, for which a projective symplectic resolution is this Hilbert scheme of endpoints on the minimal resolution of a Kleinian singularity. Okay, so the statement is this. So the linearization map is an isomorphism of vector spaces, and here it is, but that identifies the fans. I asked you earlier to bear in mind that this positive orthant, F is a fan because the hyperplane arrangement cuts it into cones. So that's a fan in the sense of toric geometry, right? So a collection of piecewise linear cones that fit together in a nice way. And this is the isomorphism of fans. So L identifies F with the movable cone of X over Y. And in what sense is this a fan? So X has an ample cone sitting in this space N1 of X over Y. So the cone comprising, or whose integral points comprise classes that are ample relative to the morphism over the base F. But any other projective crepant resolution, it's isomorphic in codimension 1 to our choice X. So the ample cones fit together nicely in the space N1 by proper transform, right? So if I have two different, let's go get on Blue Peter on you. So I've got two different projective crepant resolutions. They're isomorphic in codimension 1. So by taking the strict transform of line bundles from one to the other, not only can I identify the Picard groups, but I can see how the ample cones match up and fit together nicely. This is my fan. So this is the statement. This linearization map identifies the fans in such a way that for any chamber C, that is corresponds under this isomorphism to the ample cone of one of the models. And which model, or if you like, which projective crepant resolution is it? Well, it's the crepant resolution corresponding to any choice of theta inside the chamber C. So it's really the case that if you want to understand the birational geometry, on the one hand, which we do as an interested birational geometer, we are really saying here that it's enough just to look purely in the GIT world, look at F, and the point is, I was able to tell you what the hyperplane arrangement was. I remind you, scroll back up to this previous result, which is key, that our understanding of the GIT chamber decomposition is explicit because I know the hyperplane arrangement. So some of this is the advantage. This is the side we know, this is the side we might be interested in, and this is the side that we can understand explicitly. And another way to think about this, that I talked about the work of Maria Donten-Bury and Jarek Wiśniewski, where they're really working with Cox rings, and so in particular, when they're moving, they also give a GIT construction of these these resolutions of this C4 mod G. So this is the case n = 5 I'm talking about. And so they're working with GIT quotients constructed from the Cox rings. So they take spec of the Cox ring and let the appropriate torus act. And their choice of stability condition is moving around in here. And the point is we're working over here. So on some level, some of what we're doing is really the same. But in a sense, since we're working with quiver varieties, we're able to we can avoid doing computation because somehow there's a lot of known about Nakajima quiver varieties, and we can understand explicitly the hyperplane arrangement. But yeah, it really is two sides of the same coin on some level. So some corollaries. So the first statement is, yeah, every projective crepant resolution of the affine quotient is a hyperpolygon space. Why? Because every project, so here I have to emphasize projective crepant resolution. One expects there to be proper birational morphisms, so crepant resolutions that are proper but not projective. So Nick Proudfoot and collaborators understand many examples, certainly for hypertoric varieties, which is sort of an analogous situation. So one should expect there to be many non-projective ones, but the projective ones are those with an ample cone that's non-empty. And so the good thing is we can get all the projective ones this way, precisely because anytime you have a projective one, you walk across and choose the chamber, and that's how to choose the appropriate theta. The flip side is if you have something that's not projective, then this technique definitely doesn't capture it. A second thing, and this is the corollary I got excited about when I gave you the first choice of title, hyperpolygon spaces beyond the movable cone. That here we're saying that we understand, this isomorphism says we understand hyperpolygon spaces in the for parameters in F, which I'm thinking of as in the movable cone. But there's a subsequent result we prove where we go beyond F. So we actually understand the hyperpolygon space for any theta. And it's given by analyzing just a simple group action on the space. So I remind you, F is a positive orthant. So it has these supporting hyperplanes that are the coordinate hyperplanes. If we reflect in those coordinate hyperplanes, and that's just this group action I'm writing down, this group action is nothing more than reflection in these coordinate hyperplanes that I wrote down for you, then we're able to prove that if I have a chamber and a theta inside a chamber, when I reflect and then keep on reflecting, so any theta in the orbit of the action in my this Nakajima group, the hyperpolygon spaces are isomorphic. And in fact, conversely, any two of these spaces are isomorphic over the base. I really should say this is a statement over the base. Perhaps I'll say isomorphic over Y. If and only if I take their parameters, each theta and theta prime lies in a chamber, and the point is I want the chambers to match up under this Nakajima group action. So suddenly, so the one thing that I think is cute about this is that I've stressed that hyperpolygon spaces were studied for generic parameters in the orthant F, because those are the ones where all the parameters are non-negative, and the theta i's are lengths of edges in polygons, at least if you look at the core. And here we're saying, in fact, that you can interpret for any theta, go beyond F. A general theta, some of the entries in the stability parameter will be negative, others positive, but you can always reflect it back into the positive orthant. And in fact, if you do, the stability parameter you get to is, of course, the one you obtained by just taking the absolute values. I mean, since this is just reflection in the coordinate hyperplanes, that the one you get is just given by taking the absolute value of all the components. And so, in fact, I could write here that if you start with a theta prime and you want to find theta in F, yeah, I'll write this. So the theta prime in general corresponds to a theta in F with its components simply being the absolute value of the corresponding component of theta I prime. The conclusion then is that no matter where theta is, you can still interpret it as a hyperpolygon space, or in its core, it is still a polygon space because we have non-negative integers, namely these guys, that indicate the lengths of the edges. So, a cute curiosity. With hindsight, I felt it was perhaps a bit much to say that was to put that so centrally in the title of the talk. This perhaps is a more interesting corollary, or at least for me. So we get a simple count of the projective crepant resolutions, precisely because it's the number of chambers in F. And since we have this Nakajima group action, I can simply count the number of chambers in the entire hyperplane arrangement and then just divide by the number of elements in our group Zn to the 2, which we can certainly do. So this gives us a count of the number of projective crepant resolutions. This is a calculation one can perform. And sure enough, for n equals 5, we get 81. And yeah, there's the count for n equals 6. We failed with n equals 7. Someone who's very good at computing numbers of chambers in hyperplane arrangements may be able to do that, but we have thus far failed. But maybe 1684 is enough to be going on with. Any questions? So from this point on, I'll sketch the ideas that go into the proofs. But are there any questions at this stage about the statements or consequences? Good, all clear so far, I hope, but please don't hesitate. I shan't say much about Theorem 1 is sort of the new one. I shan't say that much about Theorem 2. Theorem 2 is this identification of the movable cone with the fan F and the consequences of that. I shan't say much because it's already largely in work that Gwyn and I did on this resolutions of this wreath product quotient. The approach is the same, and maybe there's one thing I should say. That one of the advantages, or one of the reasons to work with these hyperpolygon spaces, and indeed this is what Connor was doing, I mentioned the fact that he proved Kerwin's surjectivity in the hyperkähler context for these Nakajima quiver varieties before it was later proved in general for Nakajima quiver varieties. Right, so hyperpolygon spaces have background. They have what's the phrase I'm searching for? They have proven to be a good testing ground. They've got game. No, that's not the right phrase I'm looking for. It doesn't matter. The point is that then the approach that Gwyn and I used worked for this particular orbifolds. It also works for these Nakajima quiver varieties I'm discussing today, not all of which are orbifolds. In fact, only these two that I've highlighted before, the n equals 4 and the n equals 5 case. And so with together with Travis Schedler, we go on and we will show us work in progress that this approach works for Nakajima quiver varieties in general to really understand the birational geometry of Nakajima quiver varieties in really quite high generality. So that's sort of why one of the reasons it was worth really investigating this. It's a good testing ground to see how far one can push this. And the strategy, very briefly, is once you've got one projective crepant resolution and you're in F, and having pinned down F, it's about variation of GIT quotient. How can you detect what's happening across when you cross a wall? And we proved that for all these hyperplanes that slice through F, and these are only those of the form H capital I, then we can actually understand explicitly what's happening, at least étal locally. If we pass through if we take our theta and pass it into and then through one of the hyperplanes or through a wall that lies inside F. So in this work, we gave an étal local description of variation of GIT. And the point is it boils down to computing a very small quiver. And in this case, it's a quiver with two vertices and a collection of arrows in one direction and a collection of arrows back that enables us to understand étal locally what's happening. And so we can interpret this because we recognize the quiver as a Mukai flop, at least étal locally, and we can conclude the unstable locus from one of our hyperpolygon spaces or one of our quiver varieties has codimension greater than or equal to 2. This means that not only do we have a flop in a birational map, but more than that, these tautological line bundles from our first space, when I apply proper transform, the unstable locus has high codimension, so it's just proper transform. They don't, as they come across, they don't turn into, if you like, the tautological bundles on our adjacent moduli, or a moduli space in the adjacent chamber, are simply proper transform of the tautological bundles on our first guy. You know, there are other situations for threefold cases of quiver moduli spaces where when you do a wall crossing, the tautological bundles can undergo some quite radical, tensor by some other line bundles. And so there's quite a complicated relation between the tautological bundles on one moduli space and then the moduli space for an adjacent chamber. It might go through some sort of spherical twist. So I've studied that many, many years ago with a collaborator, Ishii. In this context, that doesn't happen. It's just proper transform. The point then is the two linearization maps. There's one map for our first chamber. There's a second map for our adjacent chamber. They're both linear maps from Qn to this narrow-Severi space. But the narrow-Severi spaces are linked by proper transform. And the point is that the maps that take as their input the tautological line bundles, they're also linked by proper transform. Put simply, the two linear maps agree. L for one chamber coincides with L for another chamber, and then you just spread throughout F, and you notice all the linearization maps agree, so you get a single globally defined linear map, and that's the one that I've called L. I called it L here, and now let me be a bit more honest. Here, I really should call it LC for the chamber C, because the choice of the bundles depends on the chamber. And somehow the point then is that this L here equals LC for any C and F. They all agree. It doesn't matter which one you take. So that's as you move through F, that's what happens. And then we can also use this étal local description that when I move to one of the boundary walls, we can check étal locally that roughly it's the product of copies of some vector space across C2 mod Z2, which gives us a divisorial contraction, at least étal locally. So you know that when you get to the boundary of F, you've actually reached, its image has reached the boundary of the movable cone. That's why we know we fill up the whole thing. Okay, so there in a sense I'm repeating some of what I've said in previous talks. The new thing, well, I mean, that's new, but it's the bit with new ideas, and I'll say this last one thing is for this first theorem about the quotient singularity. This is for the n equals 5 case, and this is this particular special case of the quiver variety here. We are just saying we've got an isomorphism of affine varieties. That shouldn't be so hard, I agree. So I should, so what do, right? So we write down both affine varieties. I understand the coordinate rings, and we want to write down a map that's an isomorphism. I agree. What we do is we write down a surjective map, and happily, right, so apply spec, I get a closed immersion from V mod G into this affine Nakajima quiver variety, but we also can compute the dimension of both of these. They're both fourfolds. So this is enough. All I have to do is construct a surjective map of the algebras. And this is a bit more involved than one might think. So I'll put up this final slide here. That is the surjective map of the coordinate rings I want to write down. So this is the coordinate ring of our affine Nakajima variety. This is our coordinate ring of our orbifold. And what we actually do, rather than write down that map, is we write down a map between two rings, two larger rings, one of which is the Cox ring of the singularity. So here, I'm writing this here. This is the Cox ring of the singularity. This was also studied in Donten-Bury and Wiśniewski's paper, and we look again at that. So we write down some. It's actually in this paper by Jürgen Hausen and Simone Krecher, explicit generators and relations for this algebra were written down. We don't need that, so we don't actually need computation at any stage in what we're doing. That's perhaps something that we should say. But this is the Cox ring of the affine singularity. This is not the Cox ring of a projective resolution. So this is not the Cox ring of x5 theta for generic theta. But it's not quite. There's a slight difference that one really should restrict here to the theta stable locus in mu inverse of 0. But it's close enough that certainly when one takes the invariant subring, so I want to, if I compute this, I can then compute this ring I care about, because there's a C star to the 5 action on, this is a C star to the 5 graded ring, and so then I look at the invariant slice, and then so we're looking at the invariant slice under this action actually recovers this guy. So we write down generators and relations for this ring, we write down an explicit surjective K-algebra homomorphism, and we note in particular that by restriction to the C star invariant part, we get a surjective map here from there to there. So that's all the n equals 5 case. And then I think, the final slide is just to invite questions. I say where we're going next, but rather than say that, I'll say, yeah, thanks. I'll stop there and see if there are any questions.